You know, when we think about predicting motion, our minds usually jump straight to forces, to acceleration, to all these complex vectors. But what if there's a more elegant way, a secret language that motion uses? Well, there is. And today we're going to decode it. We're talking about the principle of work and energy.
Okay, so you've definitely seen these yellow barrels on the highway, right? But have you ever really thought about how they work? I mean, how do a few plastic barrels stop a 2-ton car that's flying down the road? The answer, as you might have guessed, isn't just about force. It's about energy.
And that's really the big question we're tackling today. Sometimes we don't need to know the entire second-by-second story of an object's acceleration. We just want to know how fast is it going to be at the end, or how far did it travel. Tracking every single vector for that can feel like, well, it can feel like overkill. So, what if we could just follow the energy instead?
To solve this mystery, we need our first big clue. And it all starts with a word we throw around all the time, but in physics, it has a very, very specific meaning. And that word is work.
So here's the deal. In physics, work isn't about how tired you feel. You could push against a solid brick wall for hours and feel exhausted, but you've actually done zero work. Why? Because the wall didn't move. Work is only done when a force actually causes a displacement. The force and the motion have to be connected.
And here's where it gets really interesting. Work can be positive or it can be negative. Think about this crane lifting a beam. The crane's force is pulling up and the beam is moving up. They're on the same team. That's positive work. It's adding energy to the system. But now look at the car. The car is moving forward, but friction is pushing back. It's working against the motion. That's negative work. It's removing energy from the system. It's all about energy transfer.
And then, get this, some forces do no work at all. They're just kind of there. Take a block sliding across a table. The force of gravity is pulling it down, and the normal force from the table is pushing it up. But the block is moving sideways. Since those forces are perpendicular to the motion, they aren't helping it or hindering it. They're doing absolutely zero work.
Okay, so if work is the transfer of energy, what kind of energy are we actually transferring? This brings us to our second clue. We need to understand the actual currency of motion itself.
And that currency is kinetic energy. It's literally the energy of being in motion. Now look at that formula. It depends on mass, sure, but look at the velocity. It's squared. That little 2 is huge. It means if you double your speed, you don't just double your energy, you quadruple it. This is exactly why a car crash at 60 miles per hour is so much more devastating than one at 30. That squared term is no joke. The easiest way to think about kinetic energy is just as a before and after picture. We take a snapshot of the object's motion energy right at the beginning, and then we take another one at the very end. The whole story happens between those two pictures. All right, we have our clues. We've got work as the way we transfer energy, and we've got kinetic energy as the energy of motion itself. So now, let's put them together and solve this thing.
So, let's build this out, step by step. Everything starts somewhere, right? Every object begins with some amount of initial kinetic energy. That's our before snapshot. Then, stuff happens. Forces act on the object. They push, they pull, and as they do, they perform work on it, either pumping energy in or pulling energy out.
And the result of all that adding and subtracting? Well, that gives us the object's final kinetic energy. That's our after snapshot. It's really just a simple story of energy accounting.
And here it is, the whole idea, summed up in one beautiful, elegant equation. T1, that's your starting kinetic energy. Then you add up the sum of all the work done, that's the big sigma U term, and it equals T2, your final kinetic energy. Simple as that.
So why is this such a game changer? Well, look at the comparison. Newton's second law, F equals ma, is all about vectors, which can get complicated. But the work energy principle? It deals with scalars, just numbers. There's no direction to worry about. This makes the math so much simpler for a ton of problems where all we care about is the final speed or the distance traveled.
So it's one thing to know the principle. It's another thing to actually use it. How do we put this powerful idea to work to solve real problems? Well, there's a really straightforward 4-step process. First things first, you got to draw a free body diagram. You need to know every single force in play. Step 2, figure out your starting point. Calculate that initial kinetic energy, T1. Then comes the accounting phase. You go through each of those forces and calculate the work that it does.
And finally, you just plug everything into that main equation and solve for whatever you need to find.
Let's go all the way back to our crash barrels. A speeding car has a massive amount of initial kinetic energy, T1. The entire purpose of these barrels is to do a huge amount of negative work as they get crushed. They are designed specifically to remove all of that energy from the car, so that the final kinetic energy, T2, is zero. It's a perfectly engineered energy transfer.
And this principle is just incredibly versatile. It's not just for friction. It perfectly describes the work done by gravity when you go up or down a hill. It tells you exactly how much energy is stored and released by a spring. And of course, it always accounts for the energy that friction is constantly trying to steal from a system.
So let's zoom out for a second. Why is this idea so important? Why is looking at the world through the lens of work and energy so powerful?
It's because it shows us that all this complex motion we see around us is really just a beautiful, constant exchange of energy. I mean, look at a bungee jumper. As they fall, gravity does positive work, building up a ton of kinetic energy. Then, the bungee cord kicks in and does a massive amount of negative work, absorbing all that energy, right before it releases it to fling the jumper back up. It's an incredible energy dance.
And understanding this energy exchange is absolutely crucial for engineers. It's how we design safer cars. It's how we build roller coasters that are both thrilling and incredibly safe. It's how we make machines that are efficient and predictable. It's all about managing the energy.
So, I'll leave you with this thought. The next time you see a ball bounce, or maybe you're on a swing set, or you just hit the brakes in your car, think about the energy. Think about where it started, where it went, and what did the work to move it. Now that you know the secret, where do you see this great energy exchange happening all around you?